Now, apart from studying CFT for the sake of the CFTs, they are also used as tools in other problems. So, for example, due to the ADS-CFT duality, CFTs form an important part of the study of quantum gravity, where once in the ADS-CFT duality, essentially quantum gravity in ADS space is dual to CFT in one space-time dimension small. So thus, in the study of quantum gravity, albeit toy model, but it may play a very important role in the studying of quantum gravity. CFTs also form an integral part of the current holographic information theoretic investigation. So in this sense, we see that the CFTs play a very important role in the physical understanding, in the physical phenomena, ranging from phase transitions to more delicate questions of quantum gravity. Now, so with this motivation, let us now move towards understanding what a CFT is, which starts from the word conformal. So first we need to understand what is a conformal transformation. So in order to understand a conformal transformation, let us consider, first let us define the conformal transformation in a general setup. So let us consider a smooth manifold. It's a smooth manifold equipped with a Riemannian metric or maybe pseudo-Riemannian metric, it does not really matter. Now, consider a diffeomorphism of M.
Hello.
Yeah.
What is a pseudo-Riemannian metric?
Oh, so the pseudo-Riemannian metric by mean like it's like a Minkowski. So Riemannian metric is like which has a definite sign, meaning all plus or all minus. Pseudo-Riemannian meaning something like Minkowski metric, where a bunch of signs are plus and others are minus.
Okay.
Now, consider a diffeomorphism of the manifold M onto itself. Diffeomorphism means it's a smooth mapping. It's a smooth mapping of M onto it. And let's say under this diffeomorphism, the coordinates transform, let's say from x to x prime, where x prime is some function, smooth function of x. Now, such a diffeomorphism will be called a conformal transformation if it preserves the metric up to a scale factor, which is local in general. I mean, it may not be a constant scale factor, it can be a space-time dependent scale factor. So what is the mathematical statement? So the mathematical statement will be, it's tacitly represented in terms of this transformation rule. So on the left-hand side, what we have is basically how the metric transforms under the change of coordinates. And on the right-hand side, we have that what we should expect. So this factor is the local scale factor. So I've written it like exponential of some functions twice of times of sigma x. But it's a local because the scale factor here depends on x. Note that on both sides, the form of the metric is same because essentially we're considering a transformation of the same manifold. Now, it is to be emphasized here that it's a coordinate transformation. So essentially, the manifolds remains the same.
Excuse me.
Yeah.
Why this scale factor cannot be negative? Because we have taken this form exponential of something, so it says that it is positive. Why the scale factor can't be negative?
No, the overall scale factor.
Yeah.
Like e to the power 2 sigma is. You're asking why it is not negative.
Yeah, means it means we have some scale factor, say capital omega, and you are writing that capital omega in this form, e to the power some function. So by writing in this form, we are imposing in a way that this scale factor is positive.
No, yeah. So I'm imposing. It's a positive. But I think when you incorporate negative, you are basically changing the. For example, you are transforming let's say a Riemannian metric to a pseudo-Riemannian metric. You can change to it something like that, and that is something that is not. That is something that is what we are not aiming for. That essentially changes the geometry of the underlying manifold fundamentally, right? Because that's what you are doing. Because suppose you have a vector, you calculate the norm of a vector. Suppose it's positive, and then you calculate the norm of the same vector with the changed metric. Now, why that it can change in all possible way, but if it changes the sign fundamentally, that means that you're basically changing the geometry of the entire manifold. That's what we are not doing. And also, it's a smooth mapping, but changing it, the overall sign means there will be a jump in the. That's a discrete, so that's not what is possible. Okay, so
I have a
here we will.
question.
Saying it's the same metric. Even in the same manifold, if you change from say polar to Cartesian
Yes,
coordinates, your metric will
yeah,
change,
yeah, yeah,
right?
yeah. It's the same manifold.
Yeah, so it cannot be the same metric, right? After you do this transformation.
No. It's not the same metric. What I'm trying to say is that it need not be the same metric. But what I'm trying to say that if you change that sign of the total A, then it will be like you're changing the geometry of the.
Yeah. I get that. You cannot do
fundamental.
infinitesimal. You cannot get an output from an infinitesimal.
Yeah. It's not the same metric.
So
But you're
can the
labeling
sigma
them
there
by
be a
the same.
complex number?
Which one?
Can the sigma there be a complex number?
No. It's real. It's real. So this factor is a real factor.
So basically, if the scale factor is identity, we get an isometry, right?
Yes. Right. Yes.
Okay, thank you.
Okay. So we will consider conformal transformations of. So we are considering d-dimensional flat Euclidean space. So Euclidean space is the usual space. So which has a metric given by this Kronecker delta function. The conformal transformations are then defined by, it's just a trivial thing. So this is our, this is the transformation the rule that we are going to work with. Now, just from this expression, we can infer something. What you can infer is that if you calculate the Jacobian of the transformation, you can see from the previous expression, is that you can write the Jacobian of transformation as a local scaling
Can you
times
go back
rotation.
one slide?
Yeah.
Okay. Thanks.
So if you look at from that expression, you can write down the Jacobian as a local. So this is the local scaling times as a local matrix, but that matrix is essentially that belongs to the SOT. So it's basically a rotation matrix. So what does this imply is that the conformal transformation locally looks like a rigid rotation plus a scaling. But understand the importance of the word locally because this is sufficiently small neighborhood of certain point. Okay. What does geometrically conformal transformation means? Geometrically interpret a conformal transformation is something that preserves the angle between two.
Sorry, I can't hear you.
Yeah.
Parthiv, we can't hear you.
Something happening? Yeah, Bootstrap.
Just 1 second. I think he will got some internet problem. He'll come back. 1 second.
नहीं पूछने आ रहा था तुमको.
Am 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 I audible now?
Yes.
Yeah.
Sorry for this. I don't know what happened. Yeah, I think. Sorry for this. Okay. So
I think you should go back to
so
the previous slide. You have been inaudible for the last 5 minutes.
okay. So let me start from here. I guess so. This is where
Yes, I think
everything
this was
was.
where we lost you. Yes.
Okay. So what I was saying here is that geometrically, a conformal transformation preserves the angle between the two vectors, and that's what it shows that there is this grid of lines that I've shown on the left hand side. But when you give a conformal transformation, the right hand side, of course the distances have changed and lines are not even straight lines, they are now curved. But the angle between two curves, which is basically angle between the tangents to the curves, they are still same. There's the 90 degree. And that's because in conformal transformation, when you define an angle between two vectors, what you do is basically you divide the inner product by the square root of norms, and the scale factors actually cancel. So the angle gets preserved. Okay, so with the definition of the conformal transformation, we'd like to see that how the transformations actually look like. And we'll see that these transformations actually form a group. So in order to do that, so consider an infinitesimal coordinate transformation. So this is it's x mu plus epsilon mu, and epsilon is an infinitesimal quantity. This metric and infinitesimal in the sense that we are going to only retain up to terms which are single order in epsilon. And when you do this, the metric changes by this delta mu epsilon. It's basically a single derivative of epsilon. Then the conformality requires the fact that this change be proportional to the metric itself, original metric itself, which was the delta mu. This is called a conformal killing equation. If you solve the conformal killing equation for d greater than equal to 3, where we are going to focus for this lecture, there are only 4 classes of solutions. One is, so this is infinite translation, where the epsilon is essentially constant. Second, which is linear in the x, but this is infinitesimal rotation, and this is the rotation, I mean, infinitesimal rotation matrix, and this is basically anti-symmetrization. This means, so these are anti-symmetric coefficients. One is infinitesimal scaling, which is trivial, and then there is something called infinitesimal special conformal transformation. Now, this is a non-trivial bit. If I look at the finite portions, if you exponentiate them, you will find out the finite transformations. They look like so all of them are pretty much self-explanatory, but SCT is again which is a very different kind of transformation, which is very different kind. And let us see that how that looks, how these two things look like geometrically. The rotation and translations we know, but for completeness, let us look at the dilatation or scaling, constant scaling, and SCT. So the dilatations look like that. So this is a dilatation. It's basically scaling. So it's just everything becomes here expanded. You can also squeeze it. But an SCT is something which is very peculiar kind of transformation, where you can see, of course, the contours are not anymore straight line grid. But most importantly, there is one point which is like origin, which is remain fixed, and as you go more and more, the other points are getting pushed. So in a sense, SCT fixes origin, but it moves the infinity. Okay, so now let us look at how these transformations are sort of generated. What we mean by generated is that these conformal transformations are continuously connected with the identity transformation, meaning that they can be if you consider, you can consider this kind of smooth path from this transformation to the identity transformations, which is equivalent to saying that we can talk about infinitesimal conformal transformation. So they can be expressed as exponential maps of what you call the conformal generators. Thus, if capital G is a conformal transformation, then one can write capital G as an exponential of some I. There's a summation over, there's a lambda k and small gk. So small gk are basically generators. And this lambda k's are parameters which specify the transformation. It's almost like, how you specify a rotation. So there, the angular momentums are basically the generators, and the angles are the parameters. Now, this above definition implies immediately that GK, these generators are actually obtained, generators can be obtained from the transformation if you take the single derivative of the transformation with respect to the parameter. That gives you these generators. So generators are essentially the first derivative of one parameter subgroup, which is of transformations, which is essentially generated along that direction. The conformal generators.
In the chat box, Parthiv, there's a question in the chat box. What is meant by continuously connected?
Okay, continuously connected means here it's okay. The word continuously connected is really a topological term that means that in simple terms, it really means that the transformation can always be written as an identity transformation plus some other part which can be varied smoothly and which can be taken to zero smoothly. So that's what continuously connected to identity transformation means. Or equivalently, if you think of all possible transformations to kind of like a space, and each transformation has a point in that space, and identity transformation is a very specific point. Let's say, let us call it with some kind of origin of that space. Then you can draw a continuous curve from that point to the origin. So that's what continuously connected means. I hope that answers the question.
Yes.
Okay, so the conformal generators look like this. So the translation is a simple derivative. So, and rotation, these are well known from the usual Poincare algebra. The new ones are, of course, the dilatation and the special conformal transformations. Now it turns so it turns out that these generators, they actually form a Lie algebra. So these conformal generators, they actually form a Lie algebra, which I denote by this saying this small conf RT with the Lie brackets. So usually when you're defining a Lie algebra, you need to define something called Lie bracket, which is nothing but how do you multiply, it's a way of how do you multiply two elements, which is given by the usual commutator. So for example, so these two commutators are already known from the usual Poincare algebra. The new elements are this commutator, which is basically commutator of mu with k, the generators of the special conformal transformations. This d, the generator commutators of the d with all this one, and there is one with p between p mu and k mu. There is another two which I have not written because which are trivial. That's because that's the generator, that's the commuters between the different p's, which is actually zero. So they commute. Similarly, the generators of special conformal transformation, that means the different k's, they also commute. So in a sense, if you look carefully, you have within this subalgebra, you have you have two intersecting Poincare algebra. So one Poincare algebra is spanned by the angular momentum generator, so this mu news and the p's, and another Poincare algebra is basically spanned by this k's and n. So there are like two Poincare algebras, and if you pay some close attention to this these two commutators, you realize that they almost look like from the angular momentum they look very similar from the angular momentum algebra, the usual, where this p mu and k mu, they kind of act as some kind of raising and lowering operator, but no, I won't discuss that part here. Now it turns out that this algebra with everything, when you do the proper packaging, it is actually same as a Lorentz algebra. So a conformal algebra for a d-dimensional flat spacetime is a Lorentz algebra of a Minkowski space which has two more dimensions. And when you have two more dimensions, mean it has d+1 special dimension and one temporal dimension. Just to make a side comment, just to write down this thing. So if you had you considered a conformal algebra of a Minkowski space, let's say D1, then that would have been isomorphic to so that would have been isomorphic to 2. So it always becomes the Lorentz algebra, the space on which the Lorentz algebra actually acts. It always becomes one spatial dimension extra and one temporal. Okay. Another
Uh,
point here too. Yeah.
Hello. Yeah.
Yes. Yes.
Can you explain on that point a bit more? Why like it acquires a temporal dimension and this t
Oh,
plus
no, no,
one
no.
over?
Yes. So this is an observation that when you so you can basically, so this is an exercise. So basically you can repackage this uh, algebra when you do proper definition, which I have not shown here in details, but that's a long task. Then you can see that uh, it kind of that algebra becomes isomorphic to an Lorentz algebra, but there is always this one like there's always a one what would I say, negative sign of the metric that incorporates. That's just the property of the algebra. That's just an observation that you um, see something like that.
Okay. Okay.
Okay. So another thing that I would thought. So this algebraic statement, or this entire algebraic expression, they are like abstract expressions. So what we will see, we will encounter various representations of the actual this MPD matrices that will come into play. Okay. So the Lie group with the Lie algebra, this RD. So basically, what is the Lie group? That's the group of the transformation, conformal transformations. That is what is known as conformal group. So that I will just denote by this capital CONFRT, and that is also isomorphic to the Lie group SOD plus 1. And one particular subgroup of this conformal group that will play an important role at this time, it's a central role kind of the subsequent construction, is what is called a stabilizer subgroup of origin. So the more physics term is it's a kind of a little group. So it's a little group which leaves the origin invariant. That means which do not disturb the origin. We'll call this subgroup to be capital S naught. Clearly, there are three transformations which do not, so out of this four, like rotation, dilatation, and special conformal transformation, they do not change the origin. So this stabilizer subgroup of origin is actually spanned by rotation, dilatation, and special conformal transformation. Just for letter references, suppose sigma, capital sigma, and this blackboard kind of delta and kappa be the generators of this subgroup, this stabilizer subgroup or this little group, then they do form also an algebra which is actually same, which is just same from the previous. There is nothing new, so they are actually same. And so the sigmas we have already encountered in the context of or usual flat space time or usual Poincare quantum field theory. Remember that, just to give some examples, that if sigma is equal to 0 for scalars when it acts on scalars, and this is proportional to this commutator of gamma matrices when it acts on like spinors or spins. What we'll see that in the construction of conformal field theory, the representations of this S naught, that means this stabilizer subgroup, that will play a central role, or at least the way I'm going to present. So this kind of paraphrases the entire the algebraic and the group theoretic aspect of the conformal transformation. So the lessons are that the conformal transformations form a group, but most importantly, that group is also isomorphic to a certain Lorentz group in 2 dimensions, 2 space-time dimensions higher. And the algebra of the group, or the Lie algebra more precisely, of the group, they contain 2 copies of Poincare algebra. 1 copy of Poincare algebra enters into this little group algebra. So that we will make use of this. Is there any question so far?
Yes, this
Yeah.
delta and apart sigma, these are different from their counterparts D, M, and K.
No, okay. So let me just go back in the original expression. So when we wrote this expression, so there is two ways. So the way I present it is that I first calculate this M, P, K, D, etc. from the conformal transformation, and we got some certain forms, and we wrote some algebra. But once we write the algebra, this becomes a general statement. It's a statement independent of what exactly form of that M. So to answer your question precisely, that this kappa, delta, and sigma, they are different from the D, M, and K that we obtained earlier, wrote the expression. But on a more mathematical term, they actually form they actually form a they are actually representations of those conformal generators. They only act on a different space, just to say.
Okay.
Yeah. Okay. So if there's no question anymore. So next we turn to construction of conformal field theory, or what conformal field theory is, something like that. So it's a unusual. So conformal field theory, which is the theory that we are looking for, is the CFT-RD. It's a field theory, classical or quantum, and I will on RD with the space-time symmetry. So space-time symmetry means basically the underlying symmetry of the manifold. That group being given by the conformal group, and which is this conformal. Now, non-perturbatively, and I think the right thing should be said that what I mean by non-perturbatively is that, without referring without any recourse to any Lagrangian or action kind of discussion, the CFT can be described by its local field content. And what do I mean by local field? Local field meaning any local any local field structures. It is, and that's why I would like to emphasize the non-Lagrangian aspect. We are not talking about any Lagrangian. So, for example, for classical field theories, these are usual functions, and these are like usual functions, either real valued or complex valued. And for quantum CFTs, these local fields are basically local operators. So just to put some context, suppose you have a conformal field theory with an action. Suppose if let's say one example is a 5-4, one example is a what is known as a 5-4 theory, which is which has a Lagrangian simply 5-4. So here, usually this 5 field is what you can call as a fundamental field or whatever elementary field. But when we are talking about local field content of such a theory, it's not just phi, but phi square, 5-4. Not only that, even some other kind of quantity. This is also a local function. These are also local fields, and they're corresponding when we consider quantum field theory. We have the corresponding quantum operators. So that's what we mean by local field content of the theory. Now, one of the keys, I think the key statement or the key philosophy that I'm going to take is this, that the CFT or the local fields, how should we visualize this local fields? That these local fields, so these local fields are constructed as constructed to be transforming in representations of conformal group, but in a certain way. So this is like induced by the representation of the stabilizer subgroup of origin, or the that is S0, or the little group. So this kind of construction is already familiar from the usual Poincare field theory. And we are going to take almost a similar construction. So I will just illustrate this in a classical CFT construct, but it's the corresponding statements in the quantum CFT is it's pretty straightforward. So just to make the grounds, let us consider a local field phi x. So this is your phi x, some local field. It will not be some elementary field or whatever. And now consider action of any elements of the algebra, conformal algebra. Let's this curly L be that conformal algebra. And you can write down this conformal algebra, this action. Remember, this phi x is a classical field, so it's not an operator, whatever. And you can repackage it in this way, where you can essentially reduce the action to an action of an operator which I'm calling L prime on the field, but at origin, at x equal to 0. So this field I can call it's a conjugate of the L by the translation group, by the translation element. So what it really means is that what it really encapsulates is that the action of any conformal algebra element on the field at any spacetime point can be reduced to an action of a certain converted or transformed element on the field at origin. So that's where this entire stability subgroup of origin enters the picture. Now one can use the Baker-Campbell-Hausdorff formula repeatedly, and along with the commutators of the conformal algebra, to obtain the action of the conformal generators on the local field. And if you do this analysis, which is a little bit longer, then you will find out that in this expression, you will encounter these pieces. And these pieces are what the generators of the little group S0. Now, so note that on the RHS above, apart from the usual X-dependent pieces, the action of the generators of the full conformal group is essentially reduced to the action of these guys, which are the generators of the capital S0. This, in principle or in the spirit, proves our statement that what we mean by that when you say that the fields are representations which are induced from the representations of the stability subgroup. That means these group spanned by these elements. So what we need to investigate is basically a representation theory of the algebra of S0. Now it turns out, and we are interested in finite dimensional representations. So basically, we are interested in finite dimensional fields. It turns out there are two types. One is in the case when kappa mu is equal to 0. Okay, so what do I mean by kappa mu equal to 0? It's not, what I mean is that there are two kinds. So whenever you are discussing the representation of any group or any algebra, you are basically talking about constructing matrices. But that matrix, that matrix actually acts on some linear vector space. So when I'm saying this kappa mu equal to 0, what I'm really telling is that there is a vector space on which when kappa mu acts, it always gives 0. Or equivalently, this vector space is actually a kernel of the operator kappa mu. And another is this another kind of vector space is possible on which when kappa mu acts, which is the kappa mu turns out to be nilpotent. Nilpotent meaning there is some positive greater than 1, some positive integer such that if you apply kappa mu that many times on any vector from that representation space, it will give 0. I mean, you can just condense both the statements into one by just saying that kappa mu is nilpotent. The p equal to 1, the nilpotency factor, the degree of nilpotency, when that is equal to 1 is the special one, and when that is not equal to 1, that's a another class. Why the nilpotency, when the nilpotency factor P, the degree of nilpotency is equal to 1 is special? This is because when your degree of nilpotency is equal to 1, that means this statement is true. You can apply Schur's lemma to the, and when that happens, you will find out that this operator, if you remember from the algebra, let me just stare at the algebra for some minute. Yeah. So if kappa mu is equal to 0, what it really tells you is that this guy now commutes with all other elements, because already this commutes with this sigma. The only non-trivial part was this action of kappa mu. So when kappa mu is equal to 0, this whatever blackboard delta kind of, they commute with all the generators. Then I can apply the Schur's lemma, and essentially applying the Schur's lemma, I can write down this on this representation space. It is proportional to simple the identity matrix. This proportionality factor is called the scaling dimension of the operator. And such an operator for which kappa mu is equal to 0, or rather on which when you act with the kappa mu is equal to 0, is called a primary operator. So the defining property of the primary is that this kappa mu acting on phi naught equal to 0, and if you apply this capital D on phi naught and you follow the before analysis, then you will find out that that's just proportional to delta. And a field that satisfy that when you have to add more than, so just not just p equal to p greater than 0, it's actually p equal greater than 1, then that is called a descendant. So we have two kinds of fields, one is primary, another is a descendant. Now, interestingly, you can actually derive, so starting from this expression and the already expressions of the action of the algebra on the fields, you can actually derive a very simple scaling property of primary fields. It so happens that when you scale the coordinate by lambda, so phi of lambda x, that becomes equal to lambda to the power minus delta phi times phi of x. So this delta phi is again the scaling dimension, and this you can just apply the definition to the action of the algebra, and you just need to exponentiate, or rather integrate that action, and then you will find out. So there is an alternative. In this way of thinking, the way we tackle the problem is that we first look at the representation theoretic side of the conformal algebra, and from the representation theory, we argued this kind of scaling behavior. So this kind of scaling behavior. Alternatively, one could have started from this actually demand that this is my definition of primary operator. If one does that, they will also reach the same, almost similar action of the algebra action expressions, but they will essentially miss those delta and kappa mu parts, which matches with our definitions of the primary. For a general conformal transformations, meaning which is not just simple scaling, usually, and this is a general field, that means I have now allowed for some indices, non-trivial. So far I've been talking about just scalars, but now I've been also thrown in some other rotation index, meaning indices which transform non-trivially under the rotation group, and it basically transforms in this way. So there is a scaling factor, and this is the representation of the rotation matrix in which the fields actually transform. So this is the general conformal transformation property of the primary. So that's how the primary operators vary. Okay, so before I go, any questions?
Yeah, so that M, so it's M alpha beta. It's the original M, or it's just you have written it like this?
No, I've written it like this. So you can think of this M alpha beta as so you can think of this. Sorry.
No.
Sorry. Yeah. Say something.
No.
Yeah. Okay. Okay. No. So this M alpha beta is actually okay. So I've messed up the notations. So this M alpha beta is it's basically it's actually analog of the Jacobian matrix, but this R is the representation. It's in tandem with the representation of phi beta. So that means that if phi is so if he's not if he's scalar, it will be just one. But if he's, let's say, spin half or spin one, it will be some other combination, something like that.
Okay.
So, sir, I have a question. So, a few slides back, we were describing. Can you kindly go back to that? We're describing the action of the elements of the conformal algebra. So,
yeah.
I think you took the applied those L's on the fields file. Apply where L was an element of the this one.
Yeah.
So I could not. Can you a bit elaborate the second line in the after the two equations in then? So this this L becomes L prime. The one before. So
yeah. So here I have just, I mean, L prime in here, I have just kind of rearranged the stuff. So I've written the phi x as exponential of I p mu. I mean, it's just, I've just shifted I've just written it like given a translate. And what I have done then is that is basically I have imported one identity here. So what it really tells you is that L acting on phi x is equivalent to an L prime acting on phi 0, so basically at 0. But then after that, you are acting with this translation to get the x. So this part is actually telling you that this part is actually telling you to be how what will be the kind of, so L cannot, it's some part of L is actually acting on phi 0. So like x dependent part will be stripped. Those will be taken care of, these translation operators.
Can I interpret this this L to be the entire the exponential term and this L prime together clubbed up will be this L? Or
L to be the entire. So L is like L is, so what is L here? So L is basically the representation here. It's a representation of any any element of the conformal algebra on the space of functions, or on the space of fields. Okay. And what we are doing by doing all this shenanigans, what we are really doing is that we are effectively reducing that representation, or we are trying to build up that representation starting from another representation, which is L prime, but now it's a representation on the space of these fields, but the fields which are evaluated at the origin. So that's how you can interpret.
Okay. Thank you.
Hello.
Yeah.
I have a question. Are the scaling dimension and anomalous dimension same?
No, yeah. So scaling dimension, so anomalous dimension is a part of the scaling dimension. So usually scaling dimension is equal to some dimension, which is so for example, suppose so had it been a free theory, then you have some dimension, obviously, suppose, but then if you have an interaction, if you're an interacting theory, then due to that interaction, it acquires some extra dimension. That's a purely quantum effect. So scaling dimension is equal to that free theory dimension plus that what is called an anomalous dimension. So this total is actually scaling dimension.
Okay.
Okay, so okay, I don't have much time, so let me just. One of the main thing about exploiting where you can exploit the symmetries of the conformal field theory, quantum conformal theory, is that you can exploit the symmetries to write down the structures of the correlators. So let me show you just one simple example. So how we can calculate the 2-point correlators. So how can you explore the symmetry? Let's take about 2-point correlator of scalar primaries with scaling dimensions delta 1 and delta 2 respectively. Now, rotational and translational invariance requires essentially that the correlation function has to depend on the mod of the separation. So it's the absolute value of the separation of the 2 points. So this is a function of x1 minus x2 of mod. Next, the scale invariance requires that if you scale, and this is the property that we already obtained before, and then what it would imply that your f should be such function which should satisfy this kind of functional equation. And this has a solution. It's easy to check that this has a very simple power law solution, and the power law solution becomes like this. Now, if I would have stopped at just scale invariance, this would have been my final expression. But the implication of special conformal transformation is very non-trivial, and the non-triviality is it's extremely non-trivial. That's why the full invariance under full conformal group is more than the invariance under, let's say, simple scaling. So if you follow the transformation properties under the special conformal transformation, you will find out that this gives a very kind of complicated expression where something like that. But most importantly, what it does, it puts a constraint that delta 1 has to be equal to delta 2 in order to have a non-vanishing correlator. So the correlator of two primaries which have different dimensions, a 2-point function of two such primaries, will essentially vanish. Now understand this constraint that in order to have a non-vanishing 2-point correlation function, your dimensions has to be same. It's a pretty strong statement, but this entire strong statement comes from this strong statement actually is a result of requiring under the special conformal transformation. That's why that this is one point which shows that why full conformal transformation is more than just a scaling transformation. You can do the similar exercise for 3-point correlators. And so just to say that the C12s are constant coefficients which you cannot fix from the symmetry. So I think the time is, but can I get 5 minutes more just?
Yeah, you should finish
So
at a logical place.
Yeah. So 3-point correlator, you can also calculate in similar way. And you see that apart from this constant lambda 1, 2, 3, you can fix the entire other structural form, just exploiting conformal symmetry. Only the analysis is more involved than the 2-point correlator. But this impressive success actually stops for higher point functions. I mean, it stops for functions like for 4-point functions and higher point functions. And that is because for more than 3 points, you can construct conformal invariants. So conformal invariants are essentially scalar functions of n points. So which I denote here by h of xi, which are invariant under conformal transformation. So schematically you can write down that h of xi is such a function so that if g of xi is the transform coordinate, then that function is equal to the function at untransformed coordinate. So these are called conformal invariants. Because now if you have conformal invariants in your picture, you always will have some piece from purely symmetry argument. You will always can throw in pieces which are functions of these kind of conformal invariants. So let's take an example. The simplest example is a 4-point function. So let us consider a 4-point correlator of a single scalar primary. So I have just made like easy, which so they all have the same scaling dimension, but this analysis can easily be like generalized for all different dimensions. Now, with 4 points, one can construct two conformal invariants. So this I've written like U and V. And remember, these combinations, if you see that, of course, they're obviously translation, rotation, and scaling invariant. But particularly this combination, why this kind of combination comes, again, the non-trivial part will be played by the special conformal transformation. So if you now try to calculate, I mean, if you try to give a symmetry argument on the structure of the 4-point correlator, then the general form of the 4-point correlator will be like this. So this prefactor is actually fixed by these are fixed by the usual conformal symmetry argument. But now from the symmetry argument, you can also throw in any arbitrary function of uv. And when I say arbitrary, what I really mean is that you cannot fix the form of the function by symmetry arguments only, or what I call symmetry arguments / kinematical arguments only. So that's what I mean by it's an arbitrary function. So that means that using just kinematical arguments or just kinematical symmetry arguments, I cannot go beyond this. So I will always be left with this such an unknown part. And actually, the way to proceed with this proceed on this thing is the dynamics part of the theory. So you need dynamics to prove the structure. So just to summarize what we really did in this kinematical structures. So we explored the conformal symmetries and their group structures, and most importantly, we understood their algebra. Secondly, we constructed the field theoretic representations of conformal group. So we constructed the local fields of the conformal field theory as representations of conformal algebra. And because this entire construction forms the backbone of the non-perturbative formulation of CFTs, or I would rather say the non-Lagrangian formulation of the CFTs. Finally, we saw that we exploited the conformal symmetry to investigate the correlator structures in the CFTs, and we saw that we could fix 2-point and 3-point functions completely up to some constant coefficient. But the 4-point function, we saw that we could not fix completely just by the symmetry arguments, and we were left with an arbitrary part which can only be tackled using the dynamics. Okay, thank you. Yeah, that's right.
Excuse me, one question.
Yeah.
Are the high-point correlators also zero for different conformal families, or is it just the 2-point correlator?
Sorry, in the 3-point correlator you're asking?
Yeah, in the 3 and the 0.4 correlator, if the dilation constant is different, is the correlator 0 or not?
No. For 3 and 4, there is no such constraint.
Okay, thanks.
I have a question. So this the constant in the 2-point correlator and in the 3-point correlator. You like, how do you fix it dynamically, or it's just unfixed?
So these are So this 2-point correlator is a so this constant is so this is like a normalization. It's a normalization constant, but essentially, if you want to fix to a particular value, these are actually fixed with dynamically, and especially the constant term in the 3-point function that will appear extensively in the dynamics part of the story.
Okay. And which like the group theoretic first half of your slides. Like which book you mostly followed or which reference you mostly followed?
This is actually from that paper by Mack and Salam that I showed at first. So let me just so this one.
I can see it. Yeah, you have it open on the right.
Oh yes, yeah, this one. So this one. So this is the.
Okay, thanks.
So it's mostly the section 2 that I took from this paper.
Excuse me, will these notes be shared?
Yes. Yeah, this will be shared.
Yeah, so the recording of the lecture, so unfortunately it is my fault. I started recording around 5 or 6 minutes later than when he started. But rest of the lecture can be found on the website. There's a course website or whatever. There's a website that
So it will be uploaded in the YouTube channel, and the link of the YouTube channel is given in the website.
Yeah, and the course notes you can find on the website.
Yeah.
So are there any other questions? I mean, so Parthiv has also created a Slack link. So in case you want to continue discussing, you can post your questions, comments there, and maybe ask what are the best references. He might share what he has felt.
Yeah, of course. Yeah, we can discuss all this.
Yeah. And so tomorrow we will meet at the same time. Kaushik Ghosh, who is no longer a graduate student, but he did his PhD with me in the Indian Institute of Science. He's now a postdoc. So he is going to tell us. Kaushik, you should tell us what you're going to talk about tomorrow.
Yeah, so tomorrow we will cover radial quantization, operator product expansion, and we will see a little bit about conformal bootstrap, like how it constrains CFT data. So mostly Parthiv today covered most of the kinematic stuff. So we will see a bit of dynamical part of conformal field theories. So tomorrow we'll have the lecture at the same time like today. So thank you.
Okay, thank you very much. Thank you everyone for attending. All the best. Bye.
Bye.
Thank you.